Okay, so welcome to this next session. So I'm Rob and I'm chairing this, and this session is dedicated to talks focused on ice and fire. So first up, we have 4 different talks focusing on the icy stuff in UKESM, followed by 3 talks on the fire domain. First up is David talking about cryosat-2 estimates. David, if you'd like to go ahead. David, I can't hear you if you're on mute.
Can you hear me now?
Yep, I can now.
Okay.
Thank you.
Yeah, thank you and good morning, everybody. I will talk about subgrid scale sea ice thickness distribution. That means for every grid cell in the model, we do not assume the same ice thickness, but have 5 different ice thickness category in the UKESM model. So with ice thickness categories are thicknesses below 60 centimeters, between 60 centimeter 140, 140 to 240, 2.4 meters to 3.6 meter, and thicker than 3.6 meters. This is actually quite important for many processes. For example, the winter ice growth is much faster when the ice is thinner. And in summer, for the melting, if we have a lot of thin ice, this melts out much quicker, so we get a larger area of open water. The sea ice model accounts for proper transport in the ice thickness space. And there are lots of new improvements in physical parameterizations in the sea ice model, which critically depends on the sea ice thickness distribution. The issue is, it is not really, there are not many observations available to know how accurate the sea ice thickness distribution is in the model. And I will show some comparison with sea ice thickness distribution derived from the cryosat data, because there are lots of point measurements, and if we can bin when in the categories, we can for each grid cell not get just the mean ice thickness, but also the distribution. And before I look at the distribution, I show you here some data for the total ice volume. So the period here on this figure is the mean from 2011 to 2014, so which are the last 4 years of the historical simulation. I compare as you see the observations here in black for the mean ice thickness over this red area in the central Arctic. And in blue, you see 4 members from the low resolution HM3 simulation, the 4 blue lines, and you can actually see that this is for a climate model pretty perfect. So we see the annual cycle here for this 4-year period from the thickest ice in May between 2 and 3 meters, and the thinnest obviously in September. And we see that the annual cycle of the mean ice thickness from the 4 blue lines is really in good agreement with the observations. Further, I show here from the scenario runs for the near future. We see in red, green, and purple, we see quite a strong decrease of sea ice thickness in the following years. But let's look now at the, I'll move on to the next slide. But if we look just at the area of a very thick ice, and this is the ice, the fraction of a grid cell which has ice which is thicker than 3.6 meters. If you look here at the observations, we see we have hardly any thick ice in October when we have a cryosat observation. We don't have them in summer, so it's close to 0%, and it increases strongly during the winter season. And in April we have roughly 20%. If you see this black line, and if you look now at the HM3 historical simulations in blue line, we see that we have hardly any annual cycle. So the amount of thick ice, of the thickest ice, is more or less the same during the whole year. Whereas the big differences between the ensemble members, the 3 ensemble members are quite same. We have 1 ensemble member where there's much more thick ice. But the general feature is where we don't have the annual cycle we find from the observation. Well, the question is, of course, should we care about this mismatch, given that we have a mean ice volume is quite realistic? Let's look a bit of maps, how the distribution is. So on the top row, we see the observations. So the first one is for October. So we see all the blue cover is we have hardly any thick ice, less than 1% is thicker than 3.6 meters. And then this yellow is something between 1 and 5%, and the red is above orange, about 15%. So we see a strong change from here. October is the first one to January. So we have, of course, general ice growth, but it cannot just be with thermodynamics, so it's also due to ridging processes where we get a much higher fraction of thick ice, and the maximum here in April. What is in summer, we don't know from the Krauser data because we have only the winter period from October till April. So if you look at the model, which is just one of the one from the 4 example members, we see we do have quite a lot of thick ice, around 10 to 15% in October. And in a way, we get a bit of increase in the winter period, but in a way it stays more or less constant. So the thick ice survives the summer, and there's not much formation of thick ice during winter. If we look at the last figure, this is the same. We look at the ice concentration, and we did here see that the HM3 simulation was very good regarding the mean ice volume, but actually if we look at the ice concentration, we see here the black line that we only get this for this central area from the observations, a mean ice concentration about 90, a bit more than 90%, but it underestimates. All the blue lines are much lower from the ice concentration. And what we see for the future, we get if we go to the red line, this is from 2015 to 2019, so the near future from where we started the ensemble run, already quite a reduction, and within the next 20 years, we have hardly any summer sea ice. So this is in a way the same story, while the thick ice melts too slowly. So that means the end cycle of the thick ice, we keep the thick ice. The thin ice melts too fast. And the fast melt of the thin ice does cause a much more, increases the lead fraction and accelerates the summer sea ice melt. So this is in a way, this is the same story in a way, but we get in total the right, for the current conditions, the right ice growth. But due to the case that the thick ice melts too slowly and the thin ice melts too fast, if we shift that a bit, it looks quite clearly that these sea ice issues can be responsible for having too much sea ice in a slightly colder condition, so what we did observe in this historical simulation, and also has an impact on the climate sensitivity in causing the thin ice melting too fast. Thank you.
Cool, thank you. We have a couple of questions in the chat. One from Jeremy, and this was on one of the earlier slides. What happens to the fraction of thick ice in the summer after it's risen to its maximum? Yeah, I think it was on that.
In the model, in the observation, in reality.
He doesn't specify, but I think it was on the next slide.
In reality,
yeah.
In the observation.
We don't have Kaiser observations for the summer, so from this data that we don't know. In a way, we wouldn't. So we don't really know for the very thick ice in the central Arctic. Where it should be close to 0, so we wouldn't expect any thick ice there.
Cool, thank you. There's quite a lot of other questions coming in. One from Colin. Could the excess thin sea ice cause too large Arctic positive feedbacks and contribute to climate sensitivity?
Can you say it again, please?
Could the excess thin sea ice cause too large Arctic positive feedbacks and therefore contribute to the climate sensitivity?
Well, the issue is that we have too much thin ice, and when this melts too quickly, and this accelerates the feedback process in summer. So this has a potential impact on the climate sensitivity. Yes.
Cool. Lots more questions. There's lots more questions in the chat, so I think probably refer you to the Google document to answer some of those because there's quite a few coming through.
Okay. Thank you.
Cool. Thank you. Okay, next up is Robin.
Oh, okay. Hello, everyone. Oh, no, I can do this. I can do the slides very slowly. There we go. So, hello. If you heard my short update piece yesterday morning on UKESM with the Interactive Ice Sheets, this is the bit where I fill in some of the science we've got going on with the configuration. The author list here covers the team across NCAS and Bristol and Met Office and Bath, who have generally been working on the interactive ice sheets for the last few years. As I alluded to yesterday, the interactive ice sheets in global ESMs are a pretty new, complex and fraught concept for a lot of reasons. So some of the best uses for these experimental models come down to using them in an explorative kind of mode, understanding the physics and feedbacks and sensitivities. And Antony and Vicky will talk about some aspects of that after me, and that's kind of mostly what we do. But the main top-level motivation for having ice sheets in ESMs is to get joined-up projections of ice sheet contribution to sea level rise that are properly consistent with climate change predictions. In the past, ESMs couldn't do ice or other aspects of sea level. So sea level projections were assembled in a slightly ad hoc manner in separate, much later steps, often sometime after the original climate modelling was done. It was all kind of this piecemeal thing that didn't fit together terribly well. Now that we do have the ice aspects, I thought I'd take a step back from some of our exploratory stuff and give a global overview of what the current UKESM with interactive ice sheets does in terms of headline ice contributions to sea level rise globally. You can see I've got this watermark here that I've got on all of my slides from this point on, for the good reason that these results should not be taken as the last word in future sea level rise predictions. This is not the best model for doing that sort of thing. I'm illustrating the performance of one unique experimental model with a few large-scale metrics, and we're learning more about the model in the real world, really. But it's interesting to see what's going on and compare it to what we might expect. Forwards. There we go. So, Greenland first. All the results I'll be showing are from the newest configuration of UKESM ice, which runs with both ice sheets active. These Greenland only results are pretty much the same as what we saw in the ISNIP 6 runs, where we only had Greenland running though. So everything here has both ice sheets going. I'll look at them in turn. All of the results as well are relative to 2015. So sea level contributions here need to be added to what's already going on in terms of current rates of mass loss from ice sheets. In terms of the analysis, that swerves us a little bit around the coupled climate ice sheet initialization problem. So we don't need to match the currently observed rates of ice sheet mass loss if we just say we start from now and we add on to what's already going on. We do still need to worry about initialization. We need to care that any artificial model drifts don't drown out our force signal. But that's a very long discussion and I don't have time for that. So anyway, some results. Surface mass balance, snow minus melt, dominates the trend for Greenland. So the increase in mass loss from melt in SSP5 adds an additional 2–2.5 millimeters a year to sea level just on its own by 2100. Current sea level rise from all factors, including ocean heat expansion, glaciers and all the rest of it right now, is a bit over 3 millimeters a year. So in our model by 2100, SSP5 8.5, we've got additional Greenland surface melt on its own, almost doubling that. We've got some pretty small changes in calving discharge per century. That's the line here with the circles. Calving actually slows down from 2015 levels under SSP5 as the ice melts and thins near the coast. This calving trend is not the same as what's been seen in recent standalone ice sheet model runs though, and that might be indicating that we need to have an explicit marine to ice sheet coupling for Greenland and UKESM ice. The standalone ice sheet models actually increase discharge a bit, but it would take an enormous change in that discharge here to make any dent in the surface mass balance signal that overwhelms everything else. And we don't expect the calving to change that much. As we go further into the future anyway, ice retreats from the coast and calving stops being so much of a factor. So in terms of long-term future for the ice, it's not really a key issue. We are interested in long-term futures for the ice. And from a pure science view, some of the biggest coupled climate ice feedbacks start kicking in on these much longer timescales. UKESM isn't the best model to do these kind of simulations with just because it's so expensive to run the climate. We have done one run here though, using the old trick of recycling the same climate boundary conditions for a number of years while you allow the ice to run forwards before you couple them again. So you don't have to compute every New Year's climate as you go. That's much cheaper to do. So we've done this here. We've kept our warm 4 times CO2 UKESM climate constant. And over about 1,500 years, we've melted about 2/3 of Greenland. As you can see, marine coupling and carving to the coast really isn't a problem now. This is just a pure surface melt signal. This sort of run gets us back to more exploratory use of the model rather than projections per se. But it does illustrate the broad timescales we have for major ice loss from Greenland in UKESM. Next. So, there we go. All right, so we can turn now to Antarctica, which is really our kind of new toy that we have in UKESM ice. Most of the floating ice shelves around Antarctica is where the big focus is, largely because it's currently too cold in Antarctica to have significant summer melt at the surface. Melting the floating shelves doesn't add anything to sea level directly, but losing them is expected to increase the rate of ice flow upstream, so you end up flowing more ice off the continent, and that does add to sea level. To get your shelf melt right, you've got to get the oceanography around Antarctica right. We touched on this a little bit during the update yesterday, and there are problems in all models in terms of getting the Antarctic oceanography right. For the configuration here, we're using our Orca 1 ocean. Even given the limited horizontal resolution of the physics in the ice shelves it gives us, just because that's the version we've got that has water mass properties in the cavities we do resolve about right. Antony will talk a lot more about the ocean later. The dominant signal here is the emergence of widespread shelf melt in SSB5. This first kind of hits the Ross shelf, but then does later go into functional already by the end of the century. On the timescale here, we don't see a big increase in discharge of the flowing ice. So that's the circle. I mean, there's a lot of variability here, but it's not, the melting the shelves isn't massively fluxing ice off the continent. There are changes in surface mass balance too. It's not so apparent in these annual rates, but under SSP5, it's still going to be too cold to melt ice in the summer, but thermodynamically we expect an increase in snowfall and accumulation, and we do see that. Moving on. So there we go. Putting all the parts together, we can see the total additional contributions to sea level from changes in the ice sheets post-2015. So these aren't rates anymore. This is the total amount that we've added to sea level by a particular year. These were preliminary runs. We found a few bugs as we were going. So the amount of ice that actually contributes to sea level, rather than the floating stuff here, is a bit of a guess. So these are even more preliminary results than everything else. But you can see what we've got. So for SSP1, Antarctica doesn't really do much, but you're still adding about 2 centimeters onto global sea level rise just from Greenland surface melt, even at a pretty cool time. SSP 5 8.5 has a lot more. Most of this is from Greenland, so this is the global total. Greenland adds kind of 9 centimeters on its own, but that big increase in snowfall over Antarctica actually pulls sea level down by a significant amount. We'd expect this longer term Antarctic contribution to evolve in pretty non-trivial ways though, and you really need a dynamic ice model for that. We can see the ice upstream has speeded up. We've got big changes to surface mass balance. We've got thinning of the shelves downstream. Those clearly haven't played into things very much by 2100, but they're going to have a big effect pretty soon. We can compare what we've got to other estimates of future ice contributions. So we've got numbers here from the recent special report on oceans and cryosphere. And then we've got even more recent numbers split up by ice shelf from the current ISMIP 6 multi-model comparison, which is mostly standalone ice sheet models forced by kind of CNOIC class climates. So we are within, certainly, the ISMIP 6 estimates of what we'd expect for each of these ice sheets, but that isn't really saying very much.
I think that's about your time. If you could wrap up quickly, if that's okay.
Yep, so that's it. I'm done, basically.
Oh, perfect, sorry.
Vicky and Antony will go on to talk about some of the details, but if anyone's got any questions, we've got time.
Yeah, there's a couple of questions in chat. I think you answered most of them as you went along. There was one final one from Colin, just quickly. Do we have any mechanisms for assessing the risk of rapid change or thresholds being passed to the model's ice loss, i.e. in advance of the actual melt occurring? I think that links back to the tipping point stuff yesterday, I think.
Yes, we haven't really looked at that. So we haven't looked at any of the kind of the metrics that Tim was suggesting in terms of looking at autocorrelations or changes in variability. What we have seen, so that kind of almost the most sudden signal is this big jump I can go back. I can't go back. When the melting kicked off under the ice shelves and Antarctica. And we've started doing a little initial condition ensemble, and the timing of that varies really quite a lot, significantly, depending on where you've started on the ocean. So that would be an interesting case study there to see if we can see any predictors of that.
Cool, thank you. There's a few more questions in chat if I refer you to them in the Google document just to clear them up.
Cool.
Cool, yep, if we can go on to the next talk. I think it's Vicky up next to talk about atmospheric blocking and Greenland melt. Yep, go ahead.
Don't have control of the screen yet. Okay. All right, so I'm going to be talking about atmospheric blocking and Greenland melt. We're interested in atmospheric blocking over Greenland for its relationship to the surface melt of the ice sheet. And one of the things we can use to measure the blocking is the Greenland blocking index. It's an average of the 500 hectopascals geopotential between 60 and 80 degrees north and 20 to 80 degrees west in the region. And this is quite useful because it's simple to calculate in the UKESM 1 ice historical run. And when I say historical run, it's from 1970 to 2014. And there's plenty of data. So there is NCEP, NCAR, reanalysis data, daily data that runs from 1948 to present day. So we can compare those two. And so if we look at the monthly blocking index, we get very good agreement. And the root mean square of this error is 83 meters. So we've established that the historical run matches quite well with the reanalysis data. Why we're interested in the Greenland blocking is because it's been shown that in the summer, positive anomalies correspond with accelerated melt rate over the ice sheet. So summer means for June, July and August, compare them with the reanalysis. It's not bad. We get the same, pretty much the same mean across the time series, but the variation is not quite that good. Our root mean square error drops to 29 meters, but we have to appreciate in the monthly data, it's over 500 meters, but in the summer it drops to about 100 meters. So the relative error has gone up a bit. But what we want to draw your attention to is in the reanalysis, there is a positive trend from the mid-1990s, which we don't get in our model run. It's pretty flat. But then other CMIP5 models don't get it either. So we're going to then look at how that compares with the melt rate. So as I said before, anomalous Greenland blocking has been linked to the recent surface mass acceleration over Greenland. And one of the theory being is that the blocking can bring relatively warm air masses from the south and bring sunnier and drier weather conditions to enhance the melt. So if we take our top 3 values of the index, we get highs at 1991, 2004 and 2011. And the data from here on in is going to be from the historical run. So these maximums correspond very nicely to maxima in the melt rate. So if we look at what the geopotential height at 500 hectopascals looks like, so I've shown one with a minimum index, which corresponds to minimum melt at 85, and then the rest are the maximum values. So as you can see in the minimum, there's a low off the coast of northwest Greenland with cyclonic flow, that's anti-clockwise. And in the others, we have highs with anticyclonic flow. And the highs are over south southern part of Greenland, which gradually kind of move over to the southeast. And if we look at the correlation, because in the 2000s, we have high melt and high Greenland blocking. So it's not just the three maximum that seem to correlate. So from here, we do get a correlation with the summer index and the summer melt. So recently, there's been a lot of literature in the last few years that's found that Greenland blocking index is related to the cloud cover. So we're using a combination of satellite data and regional climate models. They've shown that there's a negative correlation to the cloud since the mid-1990s. So the idea being that cloud is reducing and exposing the southern part of Greenland to more sunshine. So surface shortwave radiation is increasing in the south, but they also found that there was more cloud forming in the northeast, which is leading to long wave feedback to melt as well. So if we look at the correlation that we get for the Greenland blocking index to the cloud fraction, we get a very weak correlation. And also, if we look at the time series of our cloud fraction, we actually get a positive trend in the 90s. So I think we can rule out a connection to the cloud, certainly in our case. Oh, can I have the next slide, please? Thank you.
I think it's about a minute or so left.
Sorry?
About a minute or so left.
Okay. So then we look at what's driving this. And so one of the other ideas is that warm air advection is bringing hot air, the blocking is bringing hot air onto the ice sheet. So if we look at going back to we had a positive trend in the Greenland blocking, is that we look at the annual temperature and we see that we do get a rise in temperature, if not necessarily the blocking index. But if we go back and focus on the summer, so if we look at the summer air temperature near the surface of the ice, we see it looks pretty similar to the melt rate time series. So the maximum values correspond to maxima of the temperature. And then if we look at the correlation, we get a very strong correlation with the melt rate, as you'd expect. So if we look at the correlation with the Greenland blocking, it's okay, but it's not great. But I think we can say that the atmospheric blocking is bringing the warm air onto the ice sheet. So I'm going to stop there. I have one more slide, but I'm going to stop there. So thank you very much for listening.
Thank you. I think we've got time for a question. So Colin asks, is the NSEP blocking trend truly a forced trend or a snapshot of slower natural variability?
I don't know, is the honest answer to that. I've just looked at the daily data and I've averaged it for the 3-month periods over January, June and August. So Hannah did reckon that it was a trend in the data.
Cool, thank you. There's some comments related to this in the chat, which for suggestions on things to look at and stuff, so maybe just check those out as well.
Thank you.
Cool, thank you. I think next up is Antony, who's going to be talking about the future ocean melting of the interactive Antarctic ice shelves.
Yeah, I'm gonna try to take control. So, yeah, my talk is about the future projection of the melting of the ice shelves in the UKESM and bicycles interaction. So I'm gonna start with the quickly by saying about the difference between UKESM 1 and UKESM ice. So this is the horizontal section of the UKESM 1 in an ocean coordinate model. So the white part is the Antarctic continent, and we know that in the fringe of the Antarctic there are many ice shelves, such as this, the the Ross ice shelf. In UKESM 1, the vertical section is treated as ice wall. So all the way from the ice front into the grounding line is treated as ice wall, and meltwater flux is prescribed along some of the depth, whereas in the UKESM 1 ice, we open the cavity. So from the ice front here into the grounding line, we open the cavities to represent the more real geometry, and there will be an interaction between the ocean and the ice. So the ocean will melt the ice when it's warm, and then the ice will change shape. So this is made possible through the interaction with bicycles. So with the ocean as the forcing and from atmospheric forcing from the top, it will change shape. So in terms of the component of the ESM, the difference is in UKESM 1, there's no bicycles, but in this UKESM ice interaction, we don't implement the Medusa yet. That will be in the future work. So this interaction may enable us to project the sea level rise, because the bicycles will run the dynamics and it will change the geometry and the volume. And we know like the around the continental shelf and the cavity, that's the process, the important process where the shelf dense water is produced, which is the precursor of the bottom water. So it's very important for the meridional ocean circulation. And with the changing of the topography on the top, the orography will change and the regional atmospheric process will be affected too. Hopefully this can be modeled as well. And lastly, in the future, again, with the Medusa, then we hope that we will be able to include the biogeochemical process around the Antarctic. So the scenario runs for the future projection that we have been carrying out is the 2 members for the SSP 119 and 2 members for SSP 585. So to initialize this, we used the 2 members of the UKESM 1 historical, and we used that to from year 2000, and then we do a kind of spin up to fill the data in the cavity, and also to change the shape of the ice according to the forcing. So I'm going to show the melt rate pattern. First, I show that this is the observation from the 2013, and these 2 large ice shelves here, the Ross and Fistner Run, is a cold ice shelf. So the melting there is not very significant compared to the many small ice shelves around the Amundsen Sea, where we see the red color. So in the first year of all our SSP run, the SSP 1 and SSP 5 is like this. So it's not very far from the observation. And at the end of the run for SSP 1, both of them, the first member and the second member, doesn't show a very significant difference. And this the enlarged area of the Amundsen Sea, where it's all mostly red, and this also represented in the SSP 5, but it doesn't, with the increased carbon concentration, it doesn't change the melting a lot. But the main difference are in the big ice shelf. So this is the first member of the SSP 5. So this year 2052, the red color shows that it's starting to melt. So the warm water enters through this trough, and the year 2093, melting occur in many areas, and this the last the end year of the run, and the similar thing happens, but which is very late in the run, 2093, where the Fistner run also similar the same thing, and I think if we keep running it longer, then it will also be filled with red. But with the second member of the run, this occurred much later. So there is a time delay about 25 years where it starts to melt. Sorry, this is in the run. So it starts to melt, and the year 2083. So this is the last run that we the last year that we have currently now. So surely that there is this initial condition uncertainty is very important. So we are planning to run to submit more members for this to see if the Southern Ocean variability really affect this a lot. So in terms of the melt flux, total melt flux, so this Pine Island Glacier and Thwaites are the small shelves which are in the risky situation according to the present day's runoff. So it doesn't show too much difference between SSP1 and SSP5. And this from the SSP5 where the rows jump a lot and also Filsner run. So the impact of the interaction can be seen through the anomaly between the UKESM ice and UKESM1. So I take the 2060 to 2070 mean. So this only the anomaly of the SSP5 run. So this first member and the second member. So in the sea surface temperature, we see like along the ACC, the SST is much reduced. We don't know whether this may happen. This may reduce the warm bias if we use this for the present day or historical run, but for that it will be tricky because we don't know the observation, much observation around Antarctic. And from the subsurface temperature and the heat content, it reduced the deep convection around the Weddell Gyre. And we can also see it from the anomaly of the mixed layer depth here, where it's show the blue color, and the sea ice fraction, the anomaly is proportional to the SST difference, and the ACC strength reduced about 7 to 10 Sverdrup. I know I'm not sure whether it is also partly caused by the iceberg melting or mostly by the buoyant meltwater, which changed the density structure along the ACC. I think I will give more time for questions.
Cool. Yep, I think that's about your time. We've got a couple of questions. We have one from Colin. Have you looked at the impact of ice melt on future Antarctic bottom water formation in SSP 585? So basically comparing UKESM1 to UKESM1 ice, like you've done here, but with the Antarctic bottom water.
Yeah, I think I don't show it on purpose because I in the two members, the first member showed that the bottom salinity is more saline, whereas the second one is much more fresh. So we need to submit more members for that. So yeah, I can't draw any conclusion yet.
Cool, thank you. There's a few other comments and things in the chat as well if you want to review those afterwards. Thank you. Yeah, there's more comments coming in, so definitely take a look at those. I think next up we have João, if he has control of the screen. And João will be talking about coupling the interactive fire with atmospheric composition and climate in the UKEF system model.
It looks like I have control, that's good.
Cool.
Yeah, I'll be talking about coupling fire to the atmospheric model and the composition model in the UKESM. Trying to, okay, move forward. Why are we interested in doing this? Well, the fire can exert a substantial forcing in the Earth's climate, and it's the largest source of carbonaceous aerosols globally, and it represents 60% of the primary organic carbon and black carbon aerosol emissions. It's dominant in Africa and the Amazon regions, so throughout my presentation I will mostly focus on this region and the global status of things. And in terms of to quantify how large this forcing can be, Ward et al. Has done a study, and he has shown that for the pre-industrial period, this can be as large as -1 watt per meter square. And there's quite a lot of disagreement in terms on how these feedbacks. There's not enough studies with the necessary complexity to study this, especially if we go into the regional scales of and impacts of fires. So the total radiative effect of fires on climate remains quite uncertain, and it makes it quite a relevant piece of research. So we've taken this and decided to develop and evaluate a coupled fire composition climate Earth system model using UKESM. So the coupling framework is something that looks like what's in here. We've taken the UKESM1 AMIP historical run and we coupled Inferno. So Inferno is the fire model that we are using. It takes, it's very simple. It was made with simplicity in mind, and it takes the fuel density from the land surface and soil moisture, and it uses the fire weather conditions, taking precipitation temperature, relative humidity, to calculate flammability, and merges this flammability of the vegetation with the ignitions that can come from prescribed human ignitions that are dependent on the population density and on the human development index, as well as lightning cloud-to-ground ignitions that come from the model, and it uses this to calculate a burned area. So this is the area, a fraction of land that it's burning, and using emission factors, it converts the carbon available on that land to be emitted into the atmosphere into other species like black carbon, organic carbon, carbon monoxide, and passes that to UKCA, interacting with the chemistry and with the aerosols and with the atmosphere through aerosol cloud interactions, as well as radiation. And this feedbacks to the weather, and the weather feedbacks to fire, so we close the chain in this way. One thing to note in here is this framework doesn't include any feedbacks to the vegetation, so we are always burning the same vegetation over and over again. We look at, one of the things that we are interested in is emissions for the composition model. So I'm focusing here in the biomass burning emissions of carbon monoxide and black carbon. The other ones will be very similar. The bias will be very similar because all of them depend on the available carbon to be emitted or to be burned. And on top, we have the observation data set. This comes from GFAS data. And the middle row is what we get in the model. This is the annual average. And at the bottom is the difference between the model and GFAS. On the right, we have the annual mean time series. The solid line is the model, and the dotted line is GFAS for carbon monoxide and black carbon in the bottom. And on the right, we have the climatology to show the seasonality. And one thing that we can see looking at the global plots is that the spatial distribution of the areas that we are emitting or that we are burning looks quite good, but we have large biases over Africa and in this area, this region of South America. But in general, it looks good. There's some bits that we cannot see in here is that we underestimate the fire emissions and some of the tropical peatland areas, as well as the boreal regions. But this doesn't dominate the global picture. So we focus much more on the Africa and South America regions. And we can see that in terms of climatology or seasonality, the model can reproduce the cycle quite well, although we see these overestimations during the active fire seasons, which are associated mostly with Africa. In terms of the annual means, it roughly has a similar variability found in the observations, although we get a too sharp downward trend in the emissions. Moving on. So, whoa, this is too much. Okay. Going back a bit. So we wanted to understand why are we emitting too much in Africa, especially, and we we hypothesized that this could be due to the underlying vegetation, so an excess of trees over savanna regions, which is present on the UKESM vegetation. So we did 2 experiments, one where we change 10% of the trees in a very small box over Africa to grasses, and one where we changed 50% of the trees to grasses over this tiny region. And we've
Are you still there?
Hello, Joe. Have we lost you?
I wonder whether Doug or Chantelle could step in and keep the talk moving while João tries to reconnect. If either Doug or Chantelle are there.
I'm here. I don't know what I was going to say. Where are we?
Sorry to put you on the spot. You probably know more than anyone else.
I'm afraid, I was away from the desk for a second. I was making a cup of tea.
So he was talking about changing the grass and crop percentages by faking them, basically, and seeing what effect that has.
Oh, I wasn't. It might be that he was just getting to the point that that means that we need to have interactive vegetation, and that leads into Chantelle's talk next. I think that was going to say.
That sounds like it's where it was going, yeah.
Yes. Okay. Let's just say that's what he was going to say. If he doesn't come back, me and Chantelle can try and answer any questions you have.
Cool, we've got about a minute left. Do you want to try and do the next slide, or?
So this is, oh dear, this is CO and AOD monthly mean time series in climatology. Now, what does it show? It looks pretty good to me. I'm guessing one of them is UKESM. Yeah. Well done, João. There we go.
Cool, maybe move on to the next slide.
Okay, I mean, obviously Charles is much better than me to talk about this, but I would point out that these guys haven't been working on this for very long, and these are all very promising results in a very short space of time. So maybe I'll just point that out, that it's looking great, and fire modeling's hard, and so well done.
And just point out, we have 2 follow-on talks that kind of then build upon this work even more. So I think we'll leave the questions and let João address them in the Google Docs. So if we move straight on to Chantelle next, talking about coupling fire into UKESM.
Hello, can you hear me?
Yep, that's good.
Yeah, great, thank you. Okay, so I think I've got control. Okay, so following on from João's talk, I'm going to be talking about coupling fire with all of the interactions into UKESM, so still using the same fire model Inferno. And so my work up until now has been mainly focused on coupling fire and dynamic vegetation offline in joules. So I've just got a couple of plots here showing, summarizing the effect on the terrestrial carbon cycle. So over on the left, we've got monthly percentage burned area from GFED observations compared to the joules ES runs. And you can see that the model does a pretty good job at reproducing the spatial distribution of burnt area that we see in the observations. Although there are some areas where we see too much burnt area over South America, for example, or slightly less than what we see over the African continent. And this, now we've got the additional feedbacks with dynamic vegetation. We can look at the impact on the global vegetation carbon. So these results along the top here, I should say, are from ILAM evaluations for historical and present day simulations. So on the right, it's showing the bias in vegetation carbon without fire. And we can see that there's some significant areas of high bias, which relate to too much tropical tree cover over South America and Africa, for example. And when we add in fire, then this reduces the bias over these areas. So there's a big improvement in that. We can also look at the net biome productivity as a measure of the overall carbon sink in the system. So the plot down here shows, the grey line shows net biome productivity changing over the historical period without fire, and then red is with fire. So in the present day, without fire, MVP is around 2 gigatons of carbon, and when we include fire, it reduces slightly to around 1.5. And to put this into context, the Global Carbon Project estimate that it's around 2.1 plus or minus 0.7. And from across the other land surface models that contribute towards the global carbon budget, it comes out at about 1. So we're in line with those estimates, and the point being that we maintain a carbon sink in the present day when we include fire. And we can look at a number of other measures as well for the terrestrial carbon cycle. So vegetation carbon, net primary production and gross primary production. When we include fire compared to standard run without fire, it reduces some of these measures slightly, but in the Joules ES version or configuration of Joules, we see quite high values of vegetation carbon. So this is helping somewhat and bringing it more in line with some of the observations. So we've got a model that we're quite happy with in the offline version. And so I've recently just been starting to have a look at what this might look like when we include it into the fully coupled system. So I've got here, these are the first simulations that we've done with UKESM and all of the interactions of fire. So it includes the emissions, atmospheric chemistry and lightning from João's work, and it also includes the fire mortality, so vegetation and soil burning as well, with the dynamic vegetation from my work. So I've taken a few standard runs for 4 times CO2, pre-industrial control and historical. So these are available at 11.5, so I've upgraded these to the latest versions of the UM at 11.6 and Joules 5.7 to include all of the latest work from João and myself. There's a few things to notice with the results here. So the top plot is showing the change in vegetation carbon from UKESM from 1860s to 1960s, and then as a comparison, the change in the offline Joules runs. So a few things to note. Firstly, that it's working, so it's doing what we would expect. It's reducing the vegetation carbon when we include the fire feedbacks. It has a fairly strong effect at the moment, and the other thing to note is that the pattern of vegetation loss in the coupled runs is slightly different to what we see in the offline runs, and I'll go into that in a bit more detail in a second. The time series here show vegetation carbon over the historical runs. So the black line shows the control, and I've got 2 experiments going at the moment. So one is just with the standard parameters that we use offline, and then I've been experimenting with reduced mortality from fire as well. And so for a comparison, I've got the offline vegetation carbon over the historical period here from Joules, and the line to focus on here is the blue one, the S3, which is the one with all of the forcing from climate, CO2 and land use. So you can see that the trend that we might expect is fairly stable early in the pre-industrial, and then the vegetation carbon starts to decline
2 minutes.
from around 1800. Okay, I better speed up with land use change. So these are some results. I mentioned in the previous slide that the pattern of vegetation loss is a bit different in the offline and coupled runs. So I've been trying to understand a little bit what's driving that. So I've got 4 different experiments here, JULES ES with crude ARA climates. JULES, I set up a separate run with JULES with UKESM forcing. The third row here is UKESM with fire, and then UKESM without fire. So the burnt area is the first column. You can see straight away that it's quite different in the UKESM run compared to JULES. And if we look at GFED, then the offline version is capturing a better distribution of that burnt area, and that's impacting on the vegetation carbon and fraction of vegetation cover. One of the reasons that might be happening is because the pattern of precipitation is quite different in the UKESM runs. You can see it's quite dry over this northeast coast, and that's where we're getting a high burnt area. So to look at this in a bit more detail, the plots on the left here show precipitation. So the top 2 are representing the bias that we see in UKESM. So the left one here is the ILAM valuation showing a negative precipitation bias over that northeast against CMAP observations. And then I've got a plot here showing UKESM runs and the difference between those and JULES, and it's showing the same pattern here. The one slightly below this is showing a pre-industrial control UKESM run with fire versus the JULES runs. So these are showing the additional feedbacks that fire is bringing into the system. So basically, we've got a dry climate from UKESM already over this area, and fire is making that worse. I think that's probably what we would expect from the black carbon emissions that creates a drying, and also physiological forcing, which is has been shown to be important over this area of Brazil.
That's about your time. If you could just try and wrap up.
Here. Okay, so got a couple of extra plots on ERF on the top, cloud fraction, and the top of atmosphere net downward radiation that you can have a look at, but I'll stop there. Thank you.
Cool, thank you. That was really interesting. There's some questions and comments in the chat, and there's been some attempts to answer them in the chat by Chris and Doug as well. But Colin asks, fire destroys trees, so loss of vegetation carbon, but doesn't it then allow rapid regrowth, so a rapid increase in GPP? So how do the loss and gain effects on vegetation loss and regrowth balance out? Both, I think we're talking about in the model world and in the real world. And I think Chris and Doug have started some discussion in the chat about this, but so what we do know about TRIFID, which is the vegetation model, dynamic vegetation within JULES, is it's quite slow to show regrowth. So it was meant as an equilibrium model originally. We do have work coming up in the coming years using RED, which is a demography model, which may address this a bit more, but it means when we incorporate fire, it reduces the trees, and basically we get grasses regrowing, but it takes a bit longer for the trees to come through. Do we have an understanding of what that means for the real world, though? How the real world would respond?
Yeah, so there's been quite a bit of work on savanna areas actually, and whether fire helps maintain those savanna areas. So it's still, I think the jury's out a little bit on whether fire is the primary sort of force maintaining those areas, but that's one theory, that without fire we wouldn't have savanna areas because you would get tree growth for the climate in those regions.
Cool, thank you. There's a couple more questions that have come up in chat, but if you refer to the Google Doc, they'll all be in there.
Okay. Thanks.
Cool, thank you. And then we're just moving on to Doug for the last talk in the session. And Doug's going to be talking about uncertainty and fire model parameterization. Are you on mute, Doug? Are you okay?
Sorry, when I was given control, my mute button disappeared. So can you hear me now?
Yep, it's fine.
Oh, that's a shame for you guys. Anyway, where am I? Douglas Kelley, CH. Oh, so Rob, I think we're meant to finish at 12:15, aren't we? Hopefully I won't be that far over. So I wonder if there's any fun questions for João, whether we could ask them just at the end of this as well.
Yep, so I think you've got to 12:10, and then we'll try and give João a minute or two at the end if there's any questions.
Okay, thank you. Right, I'll start now then. So these are all photos from fires in 2019, and that's my fires importance slide. This work, there's a lot of people been contributing to that, including Chantelle and João, who've been great fun to work with, so thanks guys. They've not seen the slides yet though, so don't blame them. Okay, so I'm going to be coming very much back to the land surface here. So everything, apart from one very small part at the end, is driven with observed climate. So when I talk about interannual variability and stuff, we are meant to be capturing that with these kind of things. So there is Inferno is not the only fire model out there, and over the past few decades, there's been all the major land surface models have been trying to get fire and fire dynamics incorporated into their land surface schemes. And I think it's fair to say, and I think communities say this as well, that there's a lot of problems with fire modeling at the moment when we're trying to do global fire modeling, especially for climate applications. And just a very small example in the bottom right here, just to confuse everyone where I'm starting. Two metrics which you would hope you capture when you're doing global fire modeling for climate change is your mean annual burnt area, or this applies to emissions as well. We have the same problems with emissions, but the plot shows burnt area. So mean annual burnt area and red along the x-axis, and relative trend in global burnt area as well along the y. This black dot down here is an observation. I think the mean global burnt area is a little bit more certain than relative trends. There are uncertainties on there which aren't necessarily shown in the plot, but they're not as big as the model uncertainties. And then the coloured dots are the different fire models. And you can see, apart from this this lucky one down here, fire models tend to either get too low global burnt area, weak or even positive trends, or a mixture of both. This includes Jules before João and Chantelle started working it, and I should point out that Jules looks a lot better now. And then just because everyone else, I've shown this to lots of people before, I tried to break this down to kind of what I think is three major problems. The top left one is fire models tend to not get very high burnt areas in the regions which really dominate this global signal. So let's say hell here's an example. There's a time series here. Black is a bit messy, but if you squint, you can see black is observations, and the coloured lines which come out of it fuzzy are the models. On the right hand side, though, you can see that for the height of the fire season, the climate models tend to not get some of these really, really high burnt areas and look in places which burn like completely 100% each year. Fire models tend to not pick that out. A second problem, human-dominated fire regimes like the Amazon Arca deforestation here. Although it gets the kind of seasonal timing right, the seasonality, the concentration, the length of the fire season is often quite wrong in different fire models. And internal variability is off, and again, they're not necessarily catching the right kind of maximum burnt areas as well. And then in Southeast Australia here, where it's where fire regime is completely dominated by internal variability and a lot less by seasonal variations, it's just a complete mess. And there's a good reason that fire modeling is hard. It's not, no one's done anything wrong here. It's just a really difficult thing to try and capture properly. And to try and help this, at the fire workshop, FireMet workshop last year, where we, sorry, 2018, where we set a load of the priorities for the community to try and work on. One of them was trying to develop a formal sensitivity and analysis of input parameters to try and see if fire models have the correct processes and representations, and maybe to give some confidence in fire model performance as well. And that's what we tried to do here. So we did this by kind of building a very, I'm going to call it a skeleton fire model, one with just a very basic representation of what most fire models have in common, which we call common fire. And it basically just simulates 4 main controls and burnt area: the fuel load, the flammability or the moisture of the fuel, ignitions, and fragmentation effects from people. And oh, there's a lot of plots in this slide. And start at the top left here, just to keep you on your toes. This kind of, we couple this fire model to a Bayesian inference framework. And this is the framework that really kind of gets the analysis of the underlying parameters and sensitivity of the parameters as well. So just a kind of example, in this plot in the very top left-hand corner, the blue dot there is Inferno, and it just shows that, for two parameters, the parameters don't really matter. There's one about fuel and one about moisture, but the point is there's two parameters, and fire models basically can only have one point in that parameter space, and these are often just based on literature. But for our fire model, we start off by say giving it a very uninformed prior distribution for these parameters, to say it could be anywhere in this kind of black shaded area in the background, and then we use observations to work out the probability distribution of the parameter space, which means we can also have covariant parameters as well. So this example, this fuel and moisture parameter, once we optimize it, we get this red and yellow region. And it shows there's quite a large uncertainty still on these parameters. So, you know, this fire parameter, which can fuel parameter, which can go between 0 and 100, because it's a percent, kind of makes sense, I guess, can basically be anywhere between 15 and up to 60 or 70%. And the moisture one can be like from 0 right up to 50% based on observations. If we had slightly more informed priors, that might be a bit narrower, but you know, we try to keep it as informed as possible. However, a lot of this uncertainty does collapse when you kind of build up towards burnt area. So this plot in the middle here, on the top right, is the curve which relates fuel load to burnt area, and the dotted lines are the 5 to 95% range for the posterior distribution for the parameters that go into this. And you actually see it can get quite narrow. And this plot here is a circular plot in the middle. Again, red is observations, blue is FIMIP. These ones, the FIMIP models have dynamic vegetation, so it's not necessarily a very fair comparison because we're running observed. The yellow area, though, is the model simulation based on uncertainty in these parameters. Actually, you can see it does a pretty good job of capturing the climatology in this area of deforestation in the Amazon. And then the tan area is quite an interesting thing that we're going to use for some attribution stuff. It basically shows the probability of a certain burnt area given your model results. And if you look at the time series below this, the red is again its observations. Where these observations fall within this model here, which we've just driven with meteorology, says how unusual it is based on meteorological conditions alone. So if it's kind of right near the top of the tan or shooting out the tan, it's a very unlikely fire consideration configuration.
2 minutes.
Yeah. If it's actually within the middle of that, then it's quite usual. It's like expected. And actually, just one little application we did for this. It's very hard to see, I guess. If you squint, you see there's this kind of red dots down here in this August scatter plot. This is basically showing that the observed anomaly for 2019 in August falls well outside of the posterior of the simulated, which actually says that based on meteorology alone, that was a very unusual fire month. So it might be, I don't know, sociothermal factors or something. We've also applied this for some kind of global trend analysis as well to see what's been driving recent changes in burnt area. I won't go into that now, but there's 2 papers I've got down here. If you like looking at colourful and confusing figures, then you know it's worth a look. And then just to point out that there's also some interesting relationships we can get out that we can just apply directly into fire modelling as well. So this is percentage cropland cover confusing on the x-axis here, and then changing the impact it has on burnt area in the y. And you can see that if you have like a 20% covering crop, you can reduce your burnt area by between 60 and 98%. And then this is my last slide. That was all very useful, and it's great that we got this attribution stuff because it gives us some impetus to keep going. But the purpose of this is to try and parameterize the ESM. So at the top here is just some steps we need to take the skeleton model and actually make it more Inferno-like. And at the bottom is some issues we're running into at the moment, which I'll just quickly finish on. So one of them is we have these really pretty kind of covariant plots of parameter space with different parameters changing different parameters. But actually for ESM stuff, we just want one parameter combination. So we're trying to work out how to pick that. At the moment, we're just picking the center of the blobs. However, when we do that, this approach we have at the bottom, because we then have to, when we're doing ESM modeling, we have to include the vegetation and climate biases that come with the ESM. We get this rather messy burnt area map on the right, which is nowhere near as good as this more traditional approach that Chantelle just showed. So there's still plenty of work to be done there. And I'll finish with that. Thank you very much.
Cool, thank you. We've got a couple of questions, I think. So a question from Colin. He thinks he's asked it before, but whether you've tried to include subgrid scale weather variability, e.g. gust fronts, convective rainfall, etc. in the fire models.
Not in anything. So I think there's some other fire models online. I can't think of any climate ones which necessarily do that, but there may be one. There's a few out there. So there might be some in other groups. I haven't shown anything in the results here which includes that, but more recent development of ConFire does include some representations of the distribution of not subgrid cell, sub-time step heterogeneity, and I guess we could kind of shoehorn that into sub-grid cell heterogeneity as well.
Okay, Peter asked, does the interannual variability of fire constrain some of the key unknown sensitivities?
Yes, probably. That'd be interesting to look at. I think we've got a few ideas about looking at some of the human-dominated fire regimes, how changing internal variability there might be interesting to look at for some of the socioeconomic stuff. But there's all sorts of interesting climate questions to look at that as well. I think Chantelle's had an interesting paper out recently looking at ENSO. I forget what the key results are there, but it'd be worth having a look at Burton et al. 2020 for that.
Cool, thank you. There's a couple of other questions and comments in the chat, but if João's online, I think give him a chance to answer a question or two. João, are you there?
Yes, I'm here.
Cool. Okay, you had lots of questions as you dropped out, so I'm not sure whether you've seen them or not. But I'll ask you. There's a lot, but I'll ask you a couple of them quickly.
Okay.
How are the emissions distributed vertically, and are there any plans to couple that aspect to the rest of the model?
So the gas phase emissions are emitted at the surface at the first level, as in UKCA framework, and for the organic carbon and black carbon, we include a vertical profile which is almost exponentially increasing in the vertical 20th level, model level. And the second part of the question was about? Are
there any plans to couple that aspect to the rest of the model?
That would be nice. Yes, yeah. We would need an injection height model to include the firepower and put this into the
to the chemistry and everything.
Yeah, to the chemistry and the convection as well, because fires promote convection as well. So that's a lot of things to think about, and these are very early stages to this fire modeling bit. Yeah.
Another question. So you mentioned that fire ignition was linked to population density, but isn't fire suppression also linked to population density?
Yes,
and is suppression included somehow?
Yes. So it's actually a curve. So as population increases, it increases the ignitions, but also increases the suppression. So there's a point where suppression overtakes the ignitions. So it looks like a curve. So your anthropogenic ignitions go up as population density increases and then starts to go down due to the suppression.
Okay, one last question. There's lots more to go through, so maybe check the Google Doc afterwards. But one last I'll ask now is Colin asks, have you run UKSMA with fire with observed vegetation rather than UKSM vegetation?
No, this is with the UKSM historical vegetation, modeled vegetation, and I was not aware of a configuration with observed vegetation. That would be amazing.
Cool. Okay, I think we're about time then again. And as I say, there's lots of questions, and they'll all be copied into the Google Docs for people to then go through. And you can also add any new questions into the Google Doc if there's other questions people want to ask.